You ever stop and think about how data just zips across oceans, around the world at literally the speed of light? Well, it's all thanks to this invisible backbone of fiber optic cables. Today, we're going to pull back the curtain on the hidden magic that holds that entire network together, the art and science of fusion splicing. So here's the big question, right? We're talking about joining two threads of pure glass, each one thinner than a single strand of your hair. And we have to join them so perfectly that a pulse of light doesn't even notice it's crossing from one piece to another. The level of precision needed for this is it's absolutely mind-boggling. And that's the number we're aiming for. This is the goal. A connection so seamless, so perfect, that the signal loss, that's the amount of light that gets scattered or lost at the joint, is less than 0.1 decibels. Now, to put that in perspective, that's like losing less than a single drop of water from a full bathtub. It is practically nothing.
Okay, so here's how we're going to break this down. We're going to follow the complete journey of two little fibers as they become one. We'll look at the challenge itself, the all-important prep work, that moment of fusion, how we check the connection, and of course, what happens when things go wrong.
So, to pull off this kind of microscopic magic, you can't just use any old tool. You need something special. You need the hero of our story today, the fusion splicer. Yeah, this thing is way more than just a tool. It's a precision instrument. Its entire job, its whole reason for existing, is to create a permanent, nearly invisible bond between two fibers so that light can just cruise on through without a hitch. Think of this splicer as this incredible, tiny, automated factory. You've got these V-grooves that hold the fiber perfectly still. You've got cameras that act as its eyes, and tiny micromotors that make adjustments you could never, ever make by hand. Then you have the electrodes that create the heat, and even a little oven for the final step. It's amazing how they all work together.
All right, so now that we've met the machine, let's walk through exactly what it does. The whole journey, from two fibers to one, is a very precise six-step process.
It all kicks off with preparing the fiber. Then you load it into the machine. From there, the machine takes over, handling the alignment and the fusion itself. Right after that, it actually checks its own work and gives you an estimate of how good the splice is. And finally, you protect it so it'll last for decades.
Okay, let's start with what is honestly the most critical manual part of this whole thing. Before the high-tech machine can do its magic, the fiber itself has to be prepared perfectly. Any mistake here, and the splice is doomed before you even start.
So this prep work, it's a three-part deal. First, you got to strip away all the protective layers to get down to the bare glass. Second, you clean it, usually with isopropyl alcohol, to get rid of any dust, oils, anything. And third, and this is so important, the cleave. You use a special tool to score and snap the glass, leaving a perfectly flat 90-degree end. That surface has to be flawless.
So once the fibers are prepped, this is where the technician basically steps back and lets the machine take over. The fibers get loaded into those little V-grooves, and then the machine performs what I like to call the automated handshake, a series of microscopic adjustments that are just flat out impossible for a human to do.
Now this is where you really see the difference between a high-end splicer and a cheaper one. The best ones use core alignment. Their cameras look directly at the tiny core inside the glass, the part that actually carries the light, and the motors line those up perfectly. Cheaper units just line up the outside of the glass, the cladding, which isn't nearly as precise. For things like the internet backbone, you absolutely have to have core alignment. All right, everything is prepped. Everything is perfectly lined up. Now comes the moment of truth, the climax of the entire process, where two separate strands of glass are about to become one. And it happens in a literal flash. The machine sends a high-voltage current between two tiny electrodes, creating what is essentially a tiny, perfectly controlled bolt of lightning, right where the two tips of the fiber are about to meet. This arc is going to provide some serious heat. And by serious heat, I mean, get this, that little arc heats the glass to an insane 2,000 degrees Celsius. For just a second, the glass melts, it flows together, and the machine gently pushes the ends into each other, creating one continuous, seamless strand. It's literally welding with light. Okay, the flash is over, the fibers are fused. But did it work? Is it a good connection? Well, the machine doesn't wait around to find out. It immediately runs its own quality control check. The splicer's own cameras take a good look at the new joint, checking for any little imperfections, and they calculate an estimated signal loss. It's a fantastic quick check,
But the final, official grade comes from another tool called an OTDR, which sends actual light pulses down the line to measure the connection with extreme precision.
So we've got this optically perfect connection, but here's the thing. It's still just a super fragile piece of glass. It's strong for pulling, but weak to bending. So the final step is to give it a little suit of armor so it can survive out in the real world.
And we do that with something called a heat shrink sleeve. It's this little tube that was actually slid onto the fiber way back at the beginning. You move it over the splice point, and inside it has a tiny steel rod to give it strength. Then you just pop it into the splicer's built-in oven, which heats it up, shrinks it down, and creates this hard, tough, protective shell around our perfect connection.
So that's how it's supposed to go. You know, the ideal journey. But things don't always go perfectly. Let's talk about what happens when connections fail, and the most common reasons why.
So I gotta ask, with all these different steps, the cleaning, the alignment, the arc, all of it, where do you think the process is most likely to break down? What's the #1 culprit for a bad connection?
You know, it all comes back to the very beginning. Preparation. A bad cleave, that's an end face that isn't perfectly flat and at a perfect 90-degree angle, is the single biggest cause of failure. If those two pieces of glass don't meet absolutely flush, there's no amount of fancy alignment or heat that can fix it.
Now, of course, a bad cleave isn't the only thing that can mess things up. Even a single speck of dust can ruin it. If the electrodes get worn out or dirty, they won't create a good, consistent arc. And yeah, trying to splice two totally different types of fiber together, that can be a recipe for disaster. It really all boils down to precision, cleanliness, and using the right settings for the job.
And there you have it, the journey of a fusion splice, a tiny process of stripping, cleaning, cleaving, and fusing that happens millions and millions of times a day, all over the planet, to build the very network that connects us all. This tiny, perfect weld is just one link in a massive global chain. And it kind of makes you wonder, right? What other invisible engineering marvels are hiding in plain sight, quietly powering our modern world every single day?